Notice how much like equations inequalities are. In fact, with one specific exception, we will solve inequalities the same way. Let's take a look at the first visual. We have an inequality 4x plus 3 is less than negative 5. You'll notice, as you can see the solution on the screen, that we've done the exact same thing we did in previous lessons in solving equations. That is, we subtracted 3 from both sides. Why? Because we wanted to isolate the variable expression 4x. We didn't want to know what 4x was less than. We wanted to know what x was less than. So we divided both sides by 4. X is less than negative 2. Now, we emphasized in previous lessons how important it is to check our work. How would you check that x is less than negative 2? Well, pick a number less than negative 2. For example, negative 3. Okay? And plug negative 3 into the original inequality. And you'd get negative 12 plus 3, which is negative 9, is less than negative 5. Less than, meaning to the left on the number line, negative 9 is less than negative 5, so it checks. You might also try a number that should not work. That is a number that's not less than negative 2. Let's see, let's try 0. 0 should not work. 4 times 0 is 0, plus 3 is 3. 3 is not less than negative 5. So therefore, a number that should work did, a number that should not work did not. Very important. Some difference there in checking, because remember, in inequality, there's not one answer. There's a whole smear of answers. All the numbers less than negative 2 will work. Negative 2.1, negative 3, negative 10 billion. All will be successful if you substitute that number into the original inequality. 4x plus 3 will be less than negative 5. Let's take a look at the next type of inequality, next visual, which has two differences from the first inequality we looked at. The first difference is an x on both sides. The second difference is that it's greater than or equal to. The previous one was less than. Okay? Otherwise, we solve it the same way we solved the equations in the past. What do? Well, we want to get rid of the 3x on the right side, so we subtract 3x from both sides. We want to get rid of the minus 7 on the left side, so we add 7 to both sides. We get 2x is greater than or equal to 8. We divide by 2, we get x is greater than or equal to 4. All numbers greater than or equal to 4. That means 4, because 4 is equal to 4, 4.01, 5, 6, 8, 12. Again, pick a number. As long as it's greater than or equal to 4, it should work in the original equation. In fact, I might suggest, when you have a chance, go back and check and make sure my answer is correct. I think you'll find it is. An important aspect of solving inequalities is being able to graph an inequality. And how we graph an inequality is using a number line. So first, let's go back, go to the board here, and look at what the number line looks like. The number line simply is a horizontal line that goes out in all directions, in both directions, infinite distance. Obviously, we don't have the time or the board space to go out infinite distance, so we have this arrowhead symbol in both directions, meaning it really is a line. It goes forever and ever. And someplace in the middle of that line, we have 0. All numbers to the right of 0 are your positives. The further to the right you go, the larger the positive numbers become. Positive 1, 2, 7, 12, 4 billion. To the left are the negative numbers, negative 1, negative 2. As we go further to the left, the numbers are more negative, but in terms of mathematical description, they are less, because less is to the left. A good way to remember that, in case you never could figure out what that meant, was think of temperature. Negative 6 is colder than negative 4. Yes, I know, they're both cold, but negative 6 is colder. It's further to the left, or on the thermometer, it's further down on the number line. So let's take a look at the first visual we have here on graphs. This is the graph of x is less than negative 2. Now, why is that familiar? Well, that was the solution to the first inequality we did. And notice we have drawn on the number line, we have negative 2 identified. There is a circle, it's called open circle, a non-filled in circle at negative 2, and an arrow going to the left. The arrow going to the left means less than. The open circle means not including negative 2. Because remember, the answer was x was less than negative 2. If I said to you, what was the largest number you can tell me that was less than negative 2? You might say, well, negative 2.1. Someone else over here might say negative 2.01. Someone else might say negative 2.001. And again, we'd be here forever going to negative 2.000000. Uh-oh. Who wants to do that? So the idea is we never can get how close is close. We say simply that x is less than negative 2, so it can be as close as you want to negative 2 as long as it's not negative 2, and the symbol for that is that open circle. Let's take a look at the next visual. This is a graph of the solution to our second problem. X is greater than or equal to 4. Notice two things. The arrow goes to the right because it's greater than, and the circle is colored in, which means it includes the number 4. X is greater than or equal to 4. Now, I talked about checking, but I'd like to go back and emphasize it. And let's take a look at the next visual, which starts out with the same problem we had before. And that is the first problem, 4x plus 3 is less than negative 5. The solution was x is less than negative 2. And in this case, we tried x is equal to negative 3. Why do we try that? Because negative 3 is less than negative 2. It should work. It does. Notice the check mark. On the other hand, if we tried negative 2, it doesn't work. Because, now why doesn't it work? Because remember, x has to be less than negative 2, and negative 2 doesn't work. We could also try x equals negative 1. Now, if we try x equals negative 1, and this is shown on the visual, we plug in negative 1. 4 times negative 1 is negative 4, plus 3 is negative 1. Negative 1 is not less than negative 5. So we could check numbers that should work, numbers that should not work. I've said this twice on this tape because I think it's very important that you understand this. I can't emphasize enough how important it is to check your work. Obviously, when you're doing homework problems from a textbook, in many cases the answers are in the back of the book. But on a test or in the real world, the answers are not in the back of the book because there is no book. So checking is mighty important. Okay, another thing I mentioned earlier was that there is one very significant difference between solving equations and solving inequalities. And to demonstrate what I'm talking about, let's go back to our number line. Now, in fact, let me go ahead and widen this number line just a bit to make it possibly clearer for you. Here is the number A, and here is the number B. A and B are just numbers. This could be 1 and 2 or 3 and 7. We don't know what the scale of this board is. Would you say that A was less than B? Was A equal to B, or was A greater than B? I hope you'd say that A was less than B, because A is to the left. What if I multiplied both numbers by negative 2? Well, it might be over here. Here's negative 2A, and here's negative 2B. Now, if I wrote negative 2A and negative 2B, what symbol would you put in between? Would you still put less than? And the answer, I think, is no, because you'll notice that negative 2A is to the right of negative 2B. You'd put greater than. This is the one difference. When you multiply or divide both sides of an inequality by a negative, it changes the direction of the inequality. You may have heard that in Algebra 1, and if you're already taking Algebra 2, you may have heard that, and it was just like, this was a rule that came down from the mountaintop. You know, there was a bolt of lightning, and they said, when you multiply or divide both sides of an inequality by a negative, you change the direction of inequality. There is a reason for everything in mathematics, and a very good reason here is demonstrated. When you multiply by a negative, notice what happens. The positive numbers both become negative. The number that was closer to 0, A, is still closer to 0, negative 2A. The number that was further from 0 is still further from 0. But now the number that was closer to 0 is to the right. Before it was to the left. Since it's to the right of the other number, it's greater than. Before it was to the left and it was less than. That is, when you multiply by a negative, the numbers maintain their relative position from 0. In other words, the number that was further from 0 stays further from 0. But instead of being further to the right, it's further to the left. Further to the right means greater than. Further to the left means less than. And therefore, the rule that you should remember, but now you know why it works, is that if you multiply both sides of an inequality by a negative, you must change the direction of the inequality. Less than becomes greater than, less than or equal to becomes greater than or equal to, and vice versa. So let's take a look at the next visual. The next visual has an inequality. 4 minus 2x is less than or equal to 6. We start off the same way as we did with other inequalities and equations. We subtract the 4 to isolate the negative 2x. Negative 2x is less than or equal to 2. We divide both sides by a negative 2. We are dividing by a negative. So x becomes greater than or equal to negative 1. The next thing we want to discuss is compound inequalities. What does compound mean? Compound means complex, more than one thing. These are inequalities that have more than one inequality in them. Excuse me a second. And for those who are worried, that's just water. We have the next visual, which is a compound inequality that